So this video is on everyone's favorite topic, derivations. So this is focusing on the two diffraction derivation calculations that we've talked about. So we've got our d sine theta equals m lambda and our delta y equation for the distance between adjacent maxima or minima. So firstly, let's look at the original formula. Just like with the two-slit interference, the position of the maxima can be predicted using this formula d sine theta equals m lambda. Remember that d is the distance between the grating lines, theta is the angular position of the mth maxima, so from the 0th up to whatever maxima you're talking about, that angle between the two lines is your theta. And lambda is the wavelength of the light used. M is your mth maxima or your mth order, so remember the horizontal line straight in the middle is 0, 0th order. Then we go to our first maxima is m equals 1, second maxima m equals 2. We use this formula to analyze the interference pattern produced by a diffraction grating. The derivation of d sine theta equals m lambda is one of the SACE expected outcomes. You're expected to be able to sort of explain it and derive it. So, d is equal to 1 over n for a diffraction grating of n slits per meter. The distance between them is 1 meter divided by how many slits per meter, so we need to factor that in. Also consider that the parallel rays are being brought to a focus point P on a screen. We can use similar geometry as the double slit formula derivation in this case. The first example. So this is our point P that we're talking about, and we've got our distance between the slits, and they're coming into point P. They're converging on that point. Theta is the angle from the horizontal to the maxima. So the path difference between source 1 and source 2, the difference between how far they have to travel, is this delta S. So they're calling it the difference between the two paths. It would be PS2 minus PS1. So it's the distance from here to here minus the distance from here to here. If we draw a line down, that distance is actually equal to this. This is the difference between the two paths. If this bit wasn't here, both lines would be exactly the same distance. So that's that line, this PD line, such that PS1 is equal to PD. That's our little dotted line here. Therefore, we can say that the path difference, delta S, is just S2D. So this little section here, S2 to D, this is our path difference. If you've watched the Khan Academy video already, they talk about this and they use that. He talks about it with little red lines. This is your path difference. If we consider this triangle DS1S2, so we go from here to S1 to S2, the angle DS1S2 equals theta up here. So we've got a different theta. We're just saying it's the angle between D and S1 and S1 and S2. We say that this is the angle between two lines. It's equal to the angle between their normals. In a triangle S1PD, so we go S1P to D, the angle S1PD is very small. It's basically close to 0. The angle up here is very, very, very small. This is because D is small, and therefore the length to the screen is also very large. So if this is small and you're really, really far away, this is that whole concept of like you're getting really, really close together. The further away you get, the smaller the gap gets. This angle becomes very, very tiny. Angles PS1D and PDS1, so we go from P to S1 to D and P to D to S1 in both directions, are approximately 90 degrees then. So if this angle here is 0, then these two angles must be very, very close to 90 degrees. Using that, we can say that that triangle from before, S1, S2, D, is a right angle triangle here at D. So we've now created a right angle triangle where this is your path difference, this is D, and this is just our extra line. So if we just create this triangle, S1, S2, D here, so S1, S2, D, and we consider that angle theta up there, we say that sine theta is equal to the opposite over the hypotenuse. So the opposite is this S2D side here, and the hypotenuse is the S1, S2. So that's this line here, because it's opposite. Remember, this is the right angle, so it's this side here. Then we just rearrange we get S2D divided by D, because remember this is just D. S1 to S2 is just distance D. Rearrange some of these things, S2D is equal to D sine theta, therefore delta S, which is our path difference down here, which they were calling S2D earlier, is just D sine theta. So we've got our original formula. So this is kind of a complex way to do it. There's better ways to explain this without using like S1D, S2D, things like that. That's kind of a mathematical way to describe a triangle from line to line. But this is one way to do it. So if you can explain this in a simpler version, by all means do it. But I'm going to give you a couple of alternative methods. The maxima of an interference pattern occurs when the path difference is equal to m lambda. Therefore, the angular position of the mth maxima is given by d sine theta equals m lambda. Therefore, the angular position of the m's minimum is given by d sine theta equals m plus a half lambda. So we've got our two equations we talked about. Constructive interference up here, integer times, and integer plus a half times gives us our full destructive interference. So an alternative representation. This is using the same concept. We've got our mth maxima, a point P. Here they've used, they're talking about it as m times lambda. This is just a path difference. D again. We've got our right angle triangle here. And remember in the last slide we explained why that's a right angle triangle. Because this angle is approximately 0 or very, very close to 0. Therefore, that means that these angles become 90 degrees internally. Because you've got L being so far from a very, very small distance D. So therefore, the angle becomes so sharp that it's virtually 0. So we've got our D equals 1 over n before. That's the distance between the slits is 1 meter divided by how many slits per meter for a diffraction grating? And we consider these parallel rays being brought to this focus point P again. We can use a similar geometry as the double slit formula. So this is what we're talking about now. There's an example here. Sine theta is S2 R over D, where theta is the angular displacement to the nth maxima. Therefore, d sine theta equals the path difference, PD, which is equal to m lambda. So you can condense it a bit there as well. In this example, similar concept. The length BC is the optical path difference. So this OPD is just optical path difference. The difference between one path and the other path. The length BC between the rays passing through slits A and B. BC is equal to d sine theta. If we rearrange, we're looking at BC. I could just use this triangle. If I just consider this aspect here, I've got BC. I find it by saying that BC is d sine theta. If BC is a multiple of lambda, these two rays are in phase and constructive interference will result. If BC is a multiple of lambda, DE, FG, etc., all of those are going to be multiples of lambda. For all angles where d sine theta is equal to m lambda, all of the light rays will be in phase, producing maxima at these angles. So you could take this sort of diagram and you could basically say, because L is large, D is small, the distance between slits is small, the angle between these rays up here, if they're all converging on a point, is considered to be 0 or very, very close to 0. Therefore, you create a 90 degree. Or you could use this example where you've got parallel lines coming in, you drop a normal down to the next point, and because it's a normal, it's a 90 degree triangle. This little piece here, BC, is your path difference. Then you just use a basic trigonometry. I want to know what this angle is here in terms of BC. I know that this is D, so I get my d sine theta equals this. This is the path difference, so I get my d sine theta is equal to path difference, but then I factor in this concept that they're talking about here, which is just more of a worded description. For any multiple integer of lambda, this is constructive. For any integer plus a half multiple of lambda, it's destructive interference. And I can get my d sine theta equals m lambda and d sine theta equals m plus a half lambda.
This is a bit like the two-slit experiment, but not using 2 or 3 or 4, but hundreds and hundreds of slits. If we have some form of light source and we send that light through a diffraction grating, what we get are a series of bright and dark spots on the screen. And that's what I'd like to really look through at the moment. So perhaps we have our diffraction grating over here. We get a bright spot, which we're going to call a maxima. And then there's going to be certain minimum spots. And then we have another maximum spot over here, and here, and here, and so on. Now, the one in the middle, because it's often the brightest, is called the 0th order maxima. Then we have the first order, second order, and this is a good way of working out the wavelength of light. And what we say is that d sine theta equals n lambda. Okay, and I'd like to talk through this equation now. Now, if we think about a line that joins the centre of the diffraction grating to the 0th order, and also a line that goes to the first order, the angle between the two is equal to theta. Now, we can measure this very well in the lab. Now, the good thing about using a diffraction grating to measure the wavelength of light over the two-slit experiment is that there's so many different gratings here, it lets a lot of light through. So that means it's very easy to see the bright fringes that we see over here. We can also look at the separation of the fringes. Now, on the slide here, there are 300 lines per millimetre, so d is equal to the distance between the slits. Okay, the lambda over here is the wavelength of the light, theta is this angle here, and n refers to the order of the maximum. So we might have n equals 1, n equals 2, or n equals 3, and so on. Now, if we set this up in the lab, we maybe want to find out or just confirm the wavelength of light. If you set this up so you've got a large enough distance to measure the angle theta is fairly straightforward, because we've got a triangle here with a right angle. We can measure this distance and we can measure that distance, and therefore we can calculate theta. We can maybe look at the distance from maybe the 0th to the first or second order maxima, and then we can very easily work out the distance between the slits. If we know all of that, we can work out the wavelength of the light.
Derivation number 2. So just like in the video before, we talked about this delta y aspect and figuring out the distance between that, which we can then use to figure out wavelength once we know it. Let's consider P2 to be the center of the first maxima. So this is our 0th maxima, this is the very center of the bright spot of our first maxima. The path difference from S1 and S2 at P2, so to get from this point to this point, this point, this point, just like we talked about previously, is our d sine theta equals m lambda equation. L is the distance between the slit and the screen, y is the distance, or delta y is the distance between two adjacent maxima here. As theta is taken to be very, very small, a good approximation is that sine theta is equal to, or approximately equal to, tan theta. So this is the main key here. For very small angles, sine theta is approximately equal to tan theta. Now if we construct the triangle P0, M, P2, so I go from here to the center to here, I basically just draw the triangle between these pieces here. I can use my tan theta rule now, because if sine theta is approximately equal to tan theta at very small angles, tan is useful because I've got opposite over adjacent. I don't know this side, so the sine theta is useless, but I know delta y and I know that this is L. So I get my delta y over L is equal to tan theta, but I can rearrange, and because d sine theta equals lambda, that tells me that d tan theta equals lambda. Because remember, sine theta is equal to tan theta, or approximately equal to. So I rearrange, I get my d tan theta equals lambda. I pull out some stuff, so I've taken my tan theta and I've said, well, that's the same as delta y over L from before. I've subbed that in, and I rearrange, and I get that the change in y, this distance here between the two maxima, delta y, is equal to lambda L over d. So this is how I derive my second equation for the distance between maxima or minima. We're considering bright bands, which is our reinforcement, for which d sine theta is equal to m lambda. If L is the distance from the double slits to the screen, and delta y is the distance between these two adjacent maxima and minima, because the angle theta is very small, to a really good approximation, sine theta is approximately equal to tan theta. But sine theta is equal to tan theta, which is equal to delta y over L. Therefore, that d sine theta equals m lambda becomes d delta y over L equals lambda. Rearrange, we get delta y equals lambda L over d. We call delta y the fringe separation. So I haven't been using its right term, I've been a bit lazy. Delta y is the fringe separation. It's the distance between, or the separation between, the adjacent fringes. So this is how we get it from what we talked about in this example. In both cases, it's really just a bit of trick. You find that right angle, you know two sides. The key here is that sine theta is approximately equal to tan theta. In the other example, we didn't need that piece, but this is just how we convert from a tan theta or a sine theta from our first equation into a tan theta to then rearrange and get our lambda that we want, or the delta y, for our fringe separation. So that is the derivations. If you have a look at the SACE outline, it'll tell you that you're expected to explain this. Basically, what I've done in this video is I've given you a couple of different examples. So I've given you the first one, which is potentially the most complex, and then in the second section, I've given you a much simpler version, and then for the second two, I've basically done them twice, sort of expanding on why they've done it, and I've thrown that little video in with a laser guide just because it helps sort of explain the formula in a sort of more experimental, hands-on kind of view. So if you understand these derivations or any version of it, just pick the one that makes sense to you and roll with that.
Tell me pretty lies, look me in the face, tell me that you love me.